got to record this. As an alternative to having not having the balanced chemical equation, we make assumptions. We assume that all the carbon ends up just in CO2. There are no other products. There's no soot. There's no carbon monoxide. Actually, soot and carbon monoxide would be the other potential products. And so we assume that none of the carbon forms any of that stuff. And so if you had a yellow flame, well, then that's not really valid. You're going to get errors in your analysis. And then the other thing we assume is all the hydrogen ends up here. So that, we don't know what the balanced chemical equation is, but we know, where the elements end up. But if we did have the balanced chemical equation, then you would see conservation of mass.
So just to be clear, the question number 30, when it says an unknown carbon, hydrogen, and oxygen containing compound was combusted, that's incorrect, right? Since it doesn't contain oxygen, it's just a hydrocarbon.
It says H and C, yeah.
Okay, so you wouldn't put that on the test.
Is this number 30?
Yeah, number 30 on the practice exam.
Okay. What did I say? 6260? Did I do the same?
You did the same
6260?
exact numbers.
All right, let me see. 6260, 1602. Yeah, this is my mistake. Sorry. It was not supposed to be oxygen. It's just supposed to be carbon and hydrogen. If we have carbon and hydrogen, then we don't need the total mass, right? Because we just get the ratio of carbon and hydrogen, and we figure out the simplest ratio. So, we didn't need the total mass. And so I shouldn't have written and oxygen. Otherwise, this doesn't make sense. There's only one answer, C. So anyway, I don't know what I was thinking here, but it just screwed up. So it should have been just an unknown carbon and hydrogen containing compound that's combusted. And that's probably why I left it off. I forgot to delete and oxygen.
Normally hydrocarbons, though, do have carbon, hydrogen, and oxygen. But in this case, it's just carbon.
No, normal hydrocarbons do not contain any oxygen.
I remember doing Chem for practice problems that did have unknown carbon, hydrogen, and oxygen amounts.
Okay, hydrocarbons don't normally contain, but carbon-hydrogen compounds can contain oxygen.
Okay.
In fact, there are lots of carbon, hydrogen, oxygen containing organic compounds. And it depends on what you're looking at. So these are called organic functional groups. And so we can have a list. This is just some of them. There's a lot more. But if we look at all the ones that contain, actually, this is not it. What happened to the one I was just looking at? So, if we have carbon, hydrogen, oxygen, it could be an alcohol. It could be an ether. It could be an epoxide. It could be an aldehyde. It could be a ketone. It could be a carboxylic acid. It could be an acid anhydride. It could be an ester. And more, actually. This is not a comprehensive list here. And so there are a whole bunch of organic. But the hydrocarbons are only going to contain hydrogen and carbon. And those are the red ones here. You have the alkanes, the alkenes, and the alkynes. Those are your three types of hydrocarbons.
Can you go over 32? I just want to make sure that we did it right.
This one, the molarity?
Yeah.
Did you guys, how far are you guys on chapter 4 homework?
I'm not
Didn't
even
even
done
start
with
it.
Not even done with. Okay, we're going to, because I fell behind. And so what we'll do is we'll just have chapters 1 through 3 on this test. So you can skip 4. Okay. Unless, did you study 4 or? No, all right, just chapters 1 through 3.
You didn't even really lecture.
So if that's the case, then we'll eliminate 32. Molarity you aren't going to have to do, but this is a very common calculation, going from percent by mass to molarity.
Okay. Can you just tell us what the answer is?
The answer of this one
Yeah.
is 11.7 molar.
We were kind of confused about the density, if that's grams solution or grams of pure HCl?
No, grams of solution,
Okay.
not grams of pure HCl. The percent by mass would be grams of pure HCl, so this would be 36 grams of pure HCl per 100 grams of solution.
Okay.
And then the density would be 1.18 grams of solution per milliliter of solution. Mhm.
Are we allowed any notes on the test or any papers? Bring in?
No notes, but some of the constants would give you like, gallons to liters, that kind of thing.
So we're allowed to get conversion factors on the test.
Some conversion factors I'll expect you to memorize, but
Okay.
gallons to liters and grams to pounds, I'd give you.
Okay. So we have to memorize the concepts.
Yeah, you should know the others, like centimeters to inches, you
Yeah.
should know that one for sure.
Do we need to know AMU to grams?
You should know AMU to grams because there are two reasons you should know it. One, you should know the definition of the AMU and the definition of the mole. From those two definitions, you can easily derive it. So the definition of the AMU is 12U per carbon 12 atom. And the definition of the mole has two parts to it. Okay, one part is Avogadro's number, 6.022 times 10 to the 23rd atoms per mole of atoms. And the second part is the grams. Actually, the grams came first, but using this dimensional analysis, we're going to go in this way. And that is, there's exactly, in 1 mole of carbon 12, there's exactly 12 grams. And so here the 12 cancels. The U, actually U doesn't cancel. The carbon 12 atoms cancel. The moles of carbon 12 cancel, and we're left with what? 6.022 times 10 to the 23rd U per gram. That's for anything. It doesn't have to be for carbon 12. It's just for anything. So you should know that because it's the same as Avogadro's number.
See, I may have the
And
wrong
you
number.
should memorize Avogadro's number.
Oh, I have Avogadro's number. I was curious about the number I have. It's 1.660 times 10 to the negative 29th.
That's correct also. That's what I memorized, 1.66 times 10 to the, you have it in kilograms, right?
Oh, negative 27 kilograms.
Yeah. Well, we want it in grams
Negative 29th grams.
per U. This is the number I use mainly. But I realized that, I had this number memorized at one point, but we try to minimize the amount of memorization.
Like 450.
So take this number and invert it, and then you would get this number. Or take this number and invert it. That's the inverse of Avogadro's number.
Okay.
And so the fewer things we have to memorize, the better. And so memorize either one of these is fine. Now the book goes crazy in solving some of these problems. When we get to the E equals MC squared problems, the mass is in kilograms. So what we do is we go from U to grams to kilograms. And C squared is just in meters per second. And then what this gives us is it gives us kilograms meters squared per second squared, which is a joule. But for some reason, the book, in some of the problems, wants to do this in electron volts. Electron volts is, there's a conversion factor from going from joules to electron volts. Electron volts is very popular in physics, but not as popular in chemistry. Joules is much more popular in chemistry. And so I try to keep it simple. So number 32 is chapter 4. Number 33 is chapter 4. 34 is not. 35 is chapter 4. 36 is chapter 4.
What's the answer for 35?
what is the percent yield if the actual yield is 2.85 for theoretical yield? So it would be 2.85 is what the actual yield was, divided by what you should have gotten, which is 3.15. And so 285 divided by 3.15 times 100% gives us 90.4. 90.47%. Now, 90.47% is not on there. And so we have to just pick the closest, which would be
90.6.
90.6%, right?
Yeah.
Okay. That happens. Sometimes I just copy these problems
So it's 90.6.
from the book. I don't know how they got that answer. So 90.6 would be the only answer that would be closest to that. I would double check my calculation, but it's a pretty simple calculation. Sometimes sometimes if it's within a tenth of a percent or something like that, sometimes it's due to rounding, but this one shouldn't have been. Okay.
Could you maybe just show how to do 33?
I could, but 33 is not going to be on this test at all. Do you want me to go through it?
Yes, please.
A reaction has a 70% yield. If the theoretical yield is 100 grams, how many grams is the yield? So the theoretical yield is 100 grams, but what happens is you typically only get 70% of the theoretical yield. And so that means 30% is lost. And so in this case, the answer would be 70 grams. Is we lose 30% of it, and we only have 30% of the theoretical. So it would be A would be the answer.
I had a couple of questions on the nomenclature.
Mm-hmm.
The third one, N2O, could you put dinitrogen oxide, or do you have to say monoxide?
You should say monoxide.
Okay.
The only reason is because there's lots of ones. There's N2O, N2O2, N2O4. And so there's a number of these. So it's probably best to do monoxide, dioxide, tetroxide for those.
Well, because for like carbon dioxide,
Mhm.
you don't have to say monocarbon dioxide, right?
Right.
Isn't that
But the
just-
second element, so for example here, could you just say carbon oxide? If I said carbon oxide, what am I talking about? Am I talking about CO? Or am I talking about CO2? And so it's a little bit ambiguous there. So this is
Big
why
mix.
the first element, not necessarily, but the second element, you should use mono.
Okay.
Just because there could be multiple. And in fact, when you go get your car smogged, if you have a car, if you have a ice car, they call them now,
Ice car?
ice car. Have you heard that, ice car?
No, I have not.
Me too. I didn't hear about it until somebody was talking about ice cars. And I was thinking, what are you talking about, ice car?
It should be called smoke car.
Yeah, or smoke car. Ice car means internal combustion engine car versus electric cars. And so if you have an internal combustion engine car, you bring it in to get it checked. What I think, if they're really concerned about smog, this is just my opinion, by the way, if they're really concerned about smog, they should, get rid of the old cars. The old cars pump out so much more pollution than modern internal combustion cars. So if they could subsidize, people who are driving these old beater cars that are gross polluters, they could get rid of some of those, It doesn't have to be the classic cars, but, some of those old just replace some of those. That could clean up the air quite a bit. And the other thing is diesels. They can do something, with the ships. There's a lot of ship traffic. There's a huge amount of diesel bumped out from the ship traffic, and then all the trucks. They could do something about the diesels. Then they can lower what they call the NOx. Have you heard of the NOx? NOx.
I've seen before, but I never actually read about the NOx.
The NOx are oxides of nitrogen, and there are lots. So nitrous oxide would be one of the oxides of nitrogen. This would be, X is just a variable, so NO 1/2. That would be this. Then we have NO, you know, with one oxygen. And then we have these, you know, this would be similar to that. This would be NO2, et cetera. And so when you burn nitrogen, it doesn't burn so cleanly. Like when you burn hydrocarbons, you know, it burns, like methane burns pretty cleanly to CO2, but when you try to burn nitrogen containing compounds and nitrogen, you end up with NOx. You end up with a mixture of products. And so what they do is they just categorize all those together, and that's it. The classic one is NO2. NO2 gives the brown layer of smog. You know, so if you look out, you know, out when the ships are going by, you'll see, you know, although it's kind of interesting because I was talking to, in Santa Barbara, there aren't a lot of ships, but there's a brown layer, and it looks like smog. And so these chemistry professors, there one theoretician and another guy, you know, they're just talking about this because they eat lunch at the cliff and look out at the ocean. And so they always wondered, what is that brown layer? And so what they hypothesize is that brown layer comes from the salts, you know, the spray, and some of the spray gets vaporized in the air, and then the defects in the salt, you know, defects in the salt crystal structures, and these defects in salt crystal structures can absorb certain visible light colors, which gives it a brown haze to it. And I was thinking about that, and then I was looking out, you know, out towards Catalina, you know, where the ships are, and there's a brown layer there, and I was wondering, you know, how much of that brown layer is due to these, they call them Frankel defects in the salt, versus how much is due to NOx emissions. I gotta imagine a lot's due to the NOx emissions, so, you know, those, I think those before going all electric would be, you know, good things to do. Because, you know, electricity is not like 100% clean and 100% green either. You know. But NOx, the same thing, you know, oxides of nitrogen. And so nitrogen monoxide, dinitrogen dioxide, et cetera, we're going to use that for that. The first element you don't have to, unless there's two of them. In fact, did I talk about this? They're thinking about changing all of nomenclature to the system because some chemicals typically just go by their common name. How would you name this?
Iron 3.
Iron 3.
Iron 3 oxide?
Tetroxide.
You're mixing up nomenclature rules. It's either you name it as an ionic compound. If you name it as an ionic compound, we don't use the prefix.
Yeah, it's just iron oxide.
So it's iron oxide, but what is the charge? Iron's variable charge, so what is the charge on iron?
Plus 3.
Iron 3 oxide?
Iron 3.
Iron 3 oxide actually has this formula, Fe2O3. That's iron 3 oxide or rust. So this is called rust. This is called magnetite. It's a black solid. The charge on iron in rust is 3+. The charge on iron in magnetite is
4+.
It's a fraction.
it's a fraction.
Yes.
It's not 4 because if this were -2 times 4 is -8.
Oh.
And that means 3 irons have to add up to +8. How do you get 3 irons to add up to +8? Well, that means it's iron 2 2/3. And so if we use our standard nomenclature rules, we would do iron, this is variable charge. With variable charge, we have to use Roman numerals. So we'd use iron 2 2/3 oxide. Since ionic compounds, we know the charge, we can figure out the ratio. And so if we have this. But what is iron? Is iron 2 2/3 a common charge of iron? No. And so what the mystery here is, this consists of 2 iron 3s and 1 iron 2. If I have 2 iron 3s and 1 iron 2, that's going to add up to +8. And then the 4 oxides are going to add up to -8, and then it balances. And so how do we name this? Well, it's starting to get too complicated. So some people are saying switch it, the naming system, to binary. That is, just call this tri-iron tetroxide. Tri-iron tetroxide. You can't mix and match the rules because people would get confused. Although when you look at chemical catalogs, it's easy to get all confused because everybody uses their own rules. So I was looking for ammonia. It was a European chemical catalog, and I couldn't find ammonia. And I couldn't find ammonia because they didn't call it ammonia. Do you know what they called it? They called it nitrogen trihydride. And so that's why I couldn't find ammonia. I was looking for but even nitrogen trihydride is kind of wrong. It should be called hydrogen nitride or trihydrogen nitride. You know, that would be better. Nitrogen's more electronegative, so it should get its charge. All right, so what were the other ones? Really, yeah.
Could you just explain number 4?
Number 4 in the nomenclature or number 4?
Number 4 in the problems.
The chemical properties of H1 and H2 differ. The chemical properties, this is a bit of a tricky question. For the most part, they're the same because they're both hydrogen. It's like oxygen 16, oxygen 17, oxygen 18. Each time you inhale, air, you're breathing in those 3. Is only one of those active or all 3 active? All three can be an oxidizer, and all 3 are going to form oxide, taking electrons. And so the chemical elements, this question boils down to what defines the element. What defines the element is the number of protons. The number of protons in hydrogen 1 and hydrogen 2 are the same, so they're going to behave the same. Now, there are going to be slight differences in physical properties. The one difference in physical properties is H2 weighs twice as much, so it's going to be twice as heavy. That can impact certain things, and so in the video, for the most part, they behave the same, but they're saying there are certain things that rely on in your body. I talked about that video that talked about, is drinking heavy water okay? Well, one of the things is somewhat chemical, somewhat physical, and that is sometimes the hydrogens need to break off from the water and to react. I talked about autoionization of water yesterday, in which the hydrogen broke off of water attached to another water. Well, that type of stuff happens in the body. That's called chemical exchange. The hydrogen breaks off. Well, if you have a heavier hydrogen, there's more inertia, so it slows things down a little bit. And so you don't get the same speed of those hydrolysis type reactions as you would normally get. And so having different speeds of those types of, there's other types of reactions that happen in the body, like called proton exchange, where the hydrogen moves from one position to another. Those things are going to go slower. And if they go slower, will that impact your biological reactions? And they're saying yes. And so that's probably why you don't want to drink heavy water. Although it should, for the most part, behave the same. It's just a little slower because it's heavier, twice as heavy. And so that's more physical in a way. But chemically, they should be the same.
Because I was thinking, like, the example you talked about with oxygen, where they settle at different
Yeah, that's right. That's isotopic fractionation. That's a physical process there too, but that's used to investigate where things come from. Like, for example, isotopic fractionation at the bottom of the ocean versus the top of the ocean. Do you know the composition of the water is a little different? At the bottom of the ocean, it's going to be enriched in more heavier water molecules than at the top. But it's still water. The fish can survive at the bottom of the pressures will be high, but it's going to have the same problem. And so that kind of thing is more physical. That's fractionation, and so you can detect. That's where gravity plays a role in chemistry. For the most part, gravity doesn't play much of a role, but you'll see it. And this is what geochemists study. And I actually, even though I changed my major. I did still take some geology classes at UCLA when I was there. I took cosmochemistry. That's where we studied nucleosynthesis. spent a lot of time. You know, meteorites, asteroids, that kind of stuff. And some geochemistry. And so geochemists, they're very interested in that isotopic fractionation. But, you know, certain easy applications would be ozone. You know, it's very easy to tell natural ozone in the ozone layer versus man-made ozone down here. Very easy to tell the difference if you have a mass spectrometer, because then you can quickly see what the percent abundances of each molecule is. And so you feed those samples through mass spectrometers and you can detect the differences. But you know, there's going to be differences depending on where you live, geographic. I don't know what the variation is, the variance. And so this is why when you see those percent natural abundances, those are just averages. You know, the varies, like the air composition, it varies a little bit, how much nitrogen and oxygen. You know, as you go higher up, which is heavier, an oxygen or a nitrogen?
Oxygen.
Oxygen is heavier, so if you're at the top of Everest, are you still going to have 21% oxygen? No. It's going to be a little less, you know, because oxygen's heavier, it's going to sink to the bottom of the atmosphere. But that's, again, that's physical, not necessarily chemical, so I wouldn't worry about it too much. And isotopic fractionation is I mean, it has a lot of interesting applications. So, and it's easy to do because all you need is a mass spectrometer. But anyway, isotopic fractionation is defined as the relative partitioning of the heavier and lighter isotopes between two coexisting phases in natural system. That makes sense. So it's an important tool to understand geochemical and biological systems. For example, biochemical processes cause changes in the ratio of stable carbon isotopes incorporated into biomass. Well, this is very short. Even in water vapor, vaporization, you're going to vaporize the lighter water molecules versus the heavier. And so heavier water isotopes are enriched in the liquid phase, while the lighter ones are enriched in the vapor phase. And so we see fractionation just from vaporization of water. It's not huge because the mass differences isn't so large. I mean, if one water was twice as heavy as the other, then yes, you'd see more significant fractionation. But all kinds of applications. All you need is a mass spectrometer. This is a mass spectrometer here. You can see the magnet here. This is where the things curve in their path. They go through the magnet. And then they hit the detector. The detector is probably over here. It's probably the sample. It's going this way. They don't want a whole bunch of air in here, so this is all high vacuum equipment, ultra high vacuum equipment. So they suck as much air out of the system as they can.
Looks like it would fit into the corner of the room.
Yeah. Well, our mass spectrometer is this big. It's over in the organic lab.
Oh, what the little cool stuff.
Hmm?
I said the little cool stuff.
Yeah. Well, actually, I was gonna. It was for general chemistry. They just kept it in the organic lab. This is for general chemistry because I wanted to do gasoline one other stuff, but never got around to it, unfortunately. All right. Other questions on this? Was it?
So for
So number 4 is false.
Number 4, the chemical properties differ is false. The physical properties differ, pretty much. The chemical properties should be the same.
for number 20, I just
Or
want to
close
confirm that
enough.
answer.
how many different oxygen molecules occur in nature? O16, O17, O18 naturally occur. And so you just try to figure out all the possible combinations of 16 and 17. So we're looking at O2 molecules. And so how many of them can you build? Well, we can build O16, O16. This would be the most abundant. And so when you inhale oxygen, it's mostly O16, O16. And then what? We can build O16, O17, right?
Yeah.
And then we can build O16, O18, right?
Yeah.
And then we can we build any others?
O16, O18. No, O17, O18.
O17, O18?
Yeah.
Any others?
O17, O17.
O17, O17,
O18, O18.
O18, O18. Any more that you can think of?
No. it would
No.
just be BBT.
So it's 1, 2, 3, 4, 5, 6. So number 20 would be 6 possible oxygen molecules. So each time you inhale oxygen, you're breathing all 6 of those. Are the chemical properties different? No, it's just whatever. Oxygen is oxygen. We use it to combust things. We do other things with it.
Number 24.
Number 24. What are the oxidation states? This is called trifluoroacetic acid. You don't know. You don't have to know the name. Trifluoroacetic acid is a strong acid. What makes it a strong acid compared to acetic acid, which is a weak acid? There are different ways of looking at it. One way of looking at it is by the oxidation states. And so there are 2 ways of handling this. Now, the one way is using the oxidation state rules, but the oxidation state rules give you not the individual oxidation states, they give you what? The average oxidation state. So if we use the oxidation state rules, this is what we get. So I have CF3COOH. What goes first, carbon, fluorine, oxygen, or hydrogen? Fluorine? Is it fluorine? Fluorine you would typically do first, because fluorine is so electronegative, right? But, let's see. That's correct. So the order goes what? Correct this in your notes if you wrote this. Order goes group 1, followed by fluorine, followed by hydrogen, followed by oxygen, nitrogen. Okay, so fluorine gets what? -1. Now, typically, one of the patterns that we see with the oxidation states is usually who gets the priority are the most electronegative elements. So typically, the most electronegative elements are going to get their preferred charge. The preferred charge of fluorine is -1. It likes to form like fluoride. Okay, then who goes next?
Hydrogen.
Yeah, and this is what complicates things. Normally you'd think, okay, fluorine's the most, and then oxygen would be the next most. But the reason why hydrogen gets stuck in there, and this is the main reason, is because of hydrogen peroxide. Hydrogen peroxide forces us to do hydrogen first. Otherwise, if we did oxygen and its preferred charge, which is 2 minus, then hydrogen would be 2 plus. Well, hydrogen, it's impossible for hydrogen to be 2 plus because it doesn't have 2 electrons to lose. And so we can't do oxygen first, even though we'd like to because it's quite electronegative. Here, we're going to have to do hydrogen first, plus 1. In fact, this is kind of interesting because we could do hydrogen before fluorine. It'll work as well. And so it depends on what you use. And so if we did hydrogen at plus 1, then oxygen has to be minus 1. And so here, well, we're just going to do that. Hydrogen comes before oxygen because of things like hydrogen peroxide. And then what? Oxygen would be minus 2, its preferred charge. And then we have carbon left over. And so what we'll do is we'll do X, and then this is going to be X minus 3 times minus 1, X plus 3 times minus 1, plus another X. We're not going to differentiate between the 2 carbons. And then 2 times oxygen, 2 times minus 2, plus 1 is equal to 0. The whole thing is neutral. And so this is going to give us 2x minus 3 minus 4 is minus 7 plus 1 is minus 6 is equal to 0. So x is equal to, we'll add 6 divided by 2, 3. And so it looks like the oxidation state on carbon must be plus 3. Plus 3. Okay, now when we look at the answer though,
It would be B.
plus 3 and plus 3. Do you B?
Yeah.
Well, the problem is I'm asking you them individually,
Oh,
right? And individually are they plus 3 and plus 3? No, and so this is we have to go beyond what the book did. And going beyond what the book did, we have to do the one. Do you recall the one where I drew out the Lewis structure?
Formal charge.
oh yeah.
Not for formal charge, but for oxidation state. And so what we do is we draw out the Lewis structure for this.
Yeah, that's right.
This is a carboxylic acid, but how's that? And then we do when we do formal charge, we assume this is it. There are 3 ways to count the electrons. One is Lewis octet. The other is the formal charge. The other is the oxidation state. The formal charge, we assume 100% covalent bonds. 100% covalent bonds means they're evenly shared, 50-50. In other words, it's a 50-50 split of bonding electrons. However, in oxidation state, we take the opposite extreme. What's the opposite extreme? If it's
100%.
100% ownership.
100% ionic. Here, winner takes all. Who the winner is the one that's more electronegative. But if it's a tie, then it has to be 50-50. Winner takes all. So carbon versus fluorine is not going to be a tie. Carbon versus fluorine, who's going to win? Yeah, fluorine.
Fluorine is the most electronegative.
Right, fluorine's the most electronegative element on the periodic table.
Just have to remember, up and right is more electronegative.
That leaves carbon with 0. But carbon versus carbon,
It's a tie.
that's a tie because they're both equal in terms of electronegativity. So carbon ends up with how many electrons?
One.
1. How many electrons is carbon supposed to have? 4.
4.
And so this makes it plus 3.
Professor,
Mm-hmm.
what's FC?
Oh, yeah, formal charge. OS is oxidation state. Okay, then we go to this one. Carbon versus oxygen.
Oxygen wins, yeah.
Oxygen wins.
Yeah.
And this leaves carbon with 1 electron. The carbon with 1 electron will be plus 3. But why did I say we need to do this? Because we got the same answer over here, right? The problem is you aren't always going to get the same answer here. In this case, it just worked out by coincidence. The example that I gave was different. The example that I gave was acetic acid. And the difference between acetic acid and trifluoroacetic acid is this, the hydrogens here. So if we look at acetic acid, which is HC2H3O2, what are the oxidation states? So what goes first here? Hydrogen, carbon, or oxygen? Hydrogen at plus 1. And then oxygen at minus 2. And that means we have to figure out what carbon is. And so what is carbon? 0. Now that means both of the carbons are 0. So this is 0 and this is 0. Is that correct? And so we'd say the left carbon 0, the right carbon 0. And that would be wrong, because when we do it individually, we don't want the average. We want the actual. And so in this case, the actual is going to be, well, carbon versus hydrogen, who wins?
Carbon.
Carbon. And then carbon versus carbon is going to be a tie, so one of the electrons will go to this carbon. So that leaves us with 2, 4, 6, 7 electrons. Carbon's supposed to have 4, and it has 7, therefore its oxidation state is minus 3. And then we go over to this one, carbon versus oxygen. Oxygen wins. Carbon versus carbon, it's a tie. So this carbon ends up with only 1 electron. It's supposed to have 4, so this one's going to be plus 3. So the average doesn't always work. And so we have to assign this using the structure to see. Now, there's a big difference between these two acids. Acetic acid is weak. Trifluoroacetic acid is a strong acid. And the reason is because of this. You know, this carbon's what we call electron poor, electron rich. Electron rich. This carbon over here is what we call electron poor. And so that changes the whole electronic atmosphere around this. And what it does is it makes this hydrogen even poorer. Because if these two carbons are poor, it's going to suck the electron cloud towards it, making this hydrogen more positive. And so this hydrogen has a much bigger, what we call delta plus on it, due to the change. Whereas this hydrogen has a smaller delta plus. So if you're a base, like hydroxide, which delta plus are you going to be more attracted to?
Bigger one.
The bigger one. So hydroxide is going to attack this one, making this one a stronger acid than this one. They use like trichloroacetic acid. Rather than fluorines, they put chlorines here. And you might have seen it. You could buy trichloroacetic acid like at the supermarket or the drugstore. Do you know what they use it for? Trichloroacetic acid is used for warts. Right? Have you seen that? Yeah. Try to kill those off. Anyway, other questions? So this one you should have done it using Lewis structure just to make sure, but if you did the Lewis structure or you used the rules, you came up with the same answer.
Well, shouldn't it add up to 6, right, no matter what, so it has to be B?
Well, in this case, no.
Mm-hmm. You're right.
So you don't have to do Lewis structure?
You don't.
Right, okay.
Technically you don't. But if I put in other things that add up to 6, then, yeah, then you would. Like, for example, if I did,
Second one you did, C2 is 1?
0.
Oh, 0, okay.
Let's say average, because plus 3 minus 3.
Okay.
Yeah. So there are other ways. Those are, you know, what Lily was saying, those are keys to multiple choice. In multiple choice, if you know what the reasonable answer is, then you can eliminate them, and sometimes they're nice to you, so that only one answer will work. And that way you don't have to do the full calculation. So for example, I've given multiple choice tests where I wasn't expecting somebody to do the full calculation because they could just do process elimination, but they ended up doing the full calculation. And so somebody who did that will take a lot more time. And when the exams are timed, then it makes a big difference.
How long are we gonna have for this?
A lot of time. I hate timed exams, personally. You know. But even though I hate, most of the exams I took were timed. So you're not really getting trained very well because, you know, with timed exams, you got to go through. With a timed exam, the first thing I do is scan every single question. And then I do the easy ones first and save the hardest one for last. So I figure out which one's going to be the hardest. I'm going to save that one for last and do everything else. So if I run out of time, at least I have, you know, points from the easy ones.
We do 38.
Hmm?
We do 38.
38.
Ask about
Actually, this is very similar, isn't it?
Yeah.
Dimensional alpha.
Oh yeah, wasn't that one of the problems in the first chapter? With the swimming pool?
that. Yeah, can we do 21 as well?
21.
Yeah, that's whole water as well.
Well,
Because I'm getting E. That's the one else. That's C.
Yeah, I got C.
okay. This is just a play on ppm. There are different ways that people express ppm. These are ppm by mass, not by mole. And so have you ever heard of a microgram per milliliter? A microgram per milliliter? Or a microgram per liter? So let's say you had a microgram of lead per liter of blood. How many ppm is that? So if you had a microgram of lead per liter of blood, can you figure out how many ppm that is?
Yeah.
Right. And so the way we do this is something like this. You know, we'd make an assumption that blood, the density of blood is going to be about what? The same as water. So we'd make that assumption there. And so something like this would be a microgram of blood per, a microgram of lead per liter of blood would be like this. This is the way we do these kind of things. We would do like this. So we get it in the same units. So this would be a microgram of, let's say 1 microgram of lead. Okay, then we have to figure out how many micrograms are in a liter. And so a liter we're going to assume is 1,000 grams, you know, of blood. And so this is the first thing. It's not entirely accurate, so we'll just say approximately equal. And then 1,000 grams will be how many micrograms? And so in this case, we would get microgram of lead, and then it would be 1,000 grams times how many micrograms in a gram? We'd have 1 million, 10 to the 6 micrograms per gram. And the grams cancel out. Okay, then once we get the units the same, we can convert the fraction into ppm by multiplying by a million, 10 to the 6 ppm. Just like multiplying by 100%, but instead we're multiplying by a million parts per million. And so this is going to give us 1/1000 or 0.001 ppm lead. And so these are different ways of visualizing it. And so for some people it's a lot easier to visualize. Well, if you have a microgram in a liter of blood, you know, what is that equivalent to in parts per million? Something like that. Well, what if you had a microgram of lead in 1 milliliter of blood? Okay, what we do is we make the same assumption here. We have 1 microgram of lead per, well, a milliliter of blood is equivalent to what?
1,000
No, a milliliter is equivalent to
1 liters.
how many grams of blood?
10.
We're just going to assume the blood density is close to water, and we're going to say it's going to be about
1 gram.
1 gram. Well, to convert grams into micrograms, we need to multiply by a million micrograms per gram. So grams cancel. And so now we have 1 microgram of lead per million micrograms of blood. And then we convert this into parts per million. And so we convert that into parts per million, we multiply by a million ppm. When we multiply by a million ppm, the millions cancel out, and that gives us 1 ppm of lead. And so in analytical chemistry, a microgram per milliliter is equivalent to a part per million. Do you see that?
So yours is right?
A microgram per milliliter is equivalent to a part per million.
That's a lot less. In blood.
Yeah, that's a lot. That's a microgram of lead in a milliliter of blood. It's 1 part per million lead. It's high.
Lead poison.
And so even though this question seems kind of bizarre, but a pool contains 1.2 ppm by mass chlorine. How much chlorine is in 1 kilogram of this water? So, I mean, there are different ways to do this. One way is we can go ahead and convert 1.2 micrograms of chlorine per milliliter of pool of water. That's the same thing as a ppm, if you want to. We don't have to do it this way, or we could do it the traditional way. I said you want to minimize memorization, but this is very common. This is very common, but I didn't really talk about it. So most people know that. And then we could do it, or we could just do our traditional conversion factor. Our traditional conversion factor would be 1.2 grams of chlorine per what? Million grams of water. And then we just use dimensional analysis. And so we go 1 kilogram of water to grams. This would be 1,000 grams. And then grams of water to milliliters. That would be 1,000 milliliters. And then milliliters, well, we have different units there. So we just go milliliters to grams and then just figure out how many. Or we could go milliliters to micrograms and figure out how many micrograms we have. Did somebody get the answer? Or was the answer not correct?
No.
All right, let's go ahead and do this one then.
Oh, I got B.
B?
Yeah.
Okay. Okay, 1.0 kilograms of water.
It's not me.
All right, here we're missing the data. Actually, we can go to grams. 1,000 grams per kilogram. Here we're missing the data. We need to go from grams, actually we aren't missing any data. We go from grams of water to grams of chlorine. And so 1.2 grams of chlorine per million grams of water. Okay, this is pure chlorine. So kilograms of water cancel. That leaves us grams of pure chlorine. So let's figure it out.
1.2 times 10 to the negative third.
Okay.
Or
1.2 times 10 to the negative third.
yeah.
Yeah, 10 to the third, yeah.
So yeah, we eat 1.2
Grams.
milligrams.
Of chlorine, yeah. And so, yeah, this would be 1.2 milligrams. 1.2 milligrams, if you can do that in your head, or you can convert it. E, correct answer. This one's very similar to what we did in class, right?
Chapter 1.
I think I wrote it down.
Did you want me to do this one, right?
So when you're doing the conversion factors like 1,000 grams over kilograms, do you have
You can
to,
check that.
can you leave them as is, or should we label them as, you know, chlorine or pool water or?
You can leave that as is because it works for anything. It doesn't have to be chlorine or water or whatever else.
Oh, it's 38.8.
So what are you going to start with in this number 38? 25,000 gallons of,
Swimming pool water.
yeah, pool water, PW. And then where? To liters. Okay, the liters I gave on the board. So on the board I wrote 3.785 liters per gallon. So you didn't have to memorize that. But a lot of people already had it memorized. So now they have liters of pool water. And then where? Now we're going to go to milliliters. This one you have to have memorized. How many milliliters in a liter?
1,000.
Yeah, so everybody can count this one, pretty much memorized. That gives us milliliters of pool water. Okay, now the next one is missing, right? What is the next conversion factor that has to go in here?
The density.
The density of pool water. So what we're going to have to do is we're going to have to just make a guess. What do you think the density of pool water is?
1.
Only 1. And so people use 1.1, but that's wrong. The 1.1 is not the density of pool water. The 1.1 is the density of the chlorine solution. And so what we're going to do is we're going to just assume it's going to be around 1.0. It's fairly pure pool water. And so 1.0 grams of pool water, PW, over 1 milliliter of PW. This is only good for pool water. And so this is why I write PW next to it. Whereas these are good for anything, so I don't need to write PW next to it. They work for anything. And so otherwise we couldn't have solved this problem. So we had to know that the pool water's density is going to be close to that of pure water. Okay, then we go from grams of pool water to what?
Oh, we're gonna get grams here.
Chlorine.
Yeah, grams of chlorine, because we have 1 ppm. So that we know that there's 1 gram of pure chlorine for every million grams of pool water. And so grams of pool water cancel. I wrote 1 times 10 to the 6 this time because that's what you have to punch in your calculator. And so then from grams of chlorine to what?
Milliliters chlorine, so the chlorine solution.
8%.
No, we can't. We can't go to milliliters because this is not 1.10 grams of pure chlorine. This is 1.10 grams of what?
Chlorinating solution.
Chlorinating solution.
Chlorinating.
We don't have chlorinating solution. We have grams of pure chlorine, not chlorinating solution. This is why you have to label these things much more than you have to in Chem 4 because the problems are a lot more complicated. Otherwise, you can't solve it. And so we need to go from grams of pure chlorine to something else.
8%.
Yeah, the 8%. The 8% means 8 grams of pure chlorine per 100 grams of what?
Chlorinating.
Yeah, okay.
Chlorinating solution.
Right, and so for every 100 grams of chlorinating solution, which I'll call CS, chlorinating solution, there are 8 grams of chlorine. I'm going to write this out as C. I'm not going to write Cl. I'm not going to write Cl2. I'm just going to write chlorine because I don't know where the chlorine is contained in or what it's contained in. It's probably bleach, which would be sodium hypochlorite. But in that bleach, they're going to have a number of grams. For every gram of bleach, we're going to have a certain number of grams of chlorine. And so this is why I write out chlorine all the way like this, because I don't know what the form of the chlorine is. It doesn't have to. When I say pure chlorine, it's pure chlorine atoms contained in bleach. That's what I mean by pure chlorine. All right, now we have grams of chlorinating solution. And where can we go next? Milliliter.
Here's a chlorine solution.
Yeah, for every milliliter of CS chlorinating solution, there's 1.10 grams of chlorinating solution. So the grams of chlorinating solution we cancel. And that gives us milliliters of chlorinating solution. And so let's stop here. This will tell us how many milliliters of chlorinating solution. Now, what did I assume here?
The density of water.
I assumed the
the
density of
pool.
water, and I assumed one other thing. What's the one other thing I assumed?
There's 8 grams chlorine for a chlorinating solution. We don't know if 8% is exact.
Sometimes I'll ask what assumptions were made. We didn't have to assume anything. This is not very precise. 8 means anywhere from 7.5 to 8.4. We did assume this. This is one thing we assumed. What was the other thing that we assumed?
Well, this is like the same thing with the, you have to make it an equation, because once you add in the chlorinating solution, it'll increase the volume.
Yeah, right. We assumed that, we assumed that we had 25,000 gallons, but if we're adding chlorinating solution, what's going to happen to the volume of the swimming pool? It's going to increase. And so what did I assume? I assumed that the
Amount would be so small that
The-
the
yeah,
amount
right.
of gallons in the pool would not increase.
Right, and so it depends on how many milliliters. If I'm adding 1 million milliliters, then the volume's going to change significantly. Hopefully it didn't come out to 1 million. What did it come out to?
1,075.28.
So about 1 liter. So if I added 1 liter to 25,000 gallons, is that going to make much difference in the volume? Yeah. And so that's good. Otherwise, I'd have to solve this with what?
2 formulas.
2 equations, 2 unknowns, right?
Two
Remember
equations,
doing
two-
that?
Empirical.
You guys remember doing that?
Yes.
Yeah.
Well, I mean,
So some people did that here, which is fine. That's good. So they proved it. It's good. But most people didn't do that. But if you don't do that, you got to make the assumption that the addition of this is going to have negligible impact on the total volume. Sometimes you do have to do 2 equations and 2 unknowns. Did anybody do this one? 39? 39 is, in chapter 3, is this the same question as chapter 3? 220, methanol, ethanol. Maybe it's not. Let's see what chapter 3 was. It's great if you can get through the homework problems quickly so that you have time to review them. The more time you have to review this kind of stuff, the better.
It's the one that you erased because I think what threw me off was
Actually, there's other problems that I think are pretty interesting. There's a part per billion problem in here. Did you see that one? Part per billion? part per billion and part per million are the same thing. The only difference is you multiply by billion instead of a million. And then the fraction is going to be per billion rather than per million.
976.
And so the part per billion one was let's see where it was, the chloroform in water, drinking water. You know, I had all these open before I shut down my computer.
Which browser did you have it open on?
Oh, that's true. I had it open on Chrome, so I probably can just go back.
I see it. 100. Maybe? Oh.
Check your usage.
Part per billion ppb.
You can just like control.
I thought it was
That's all right.
100.
95. 95 has PP.
Yeah, it wasn't 95.
I thought it was number 100.
Oh, here it is, number 97. This is the one I was looking for. 97, published water supply was found to contain 0.8 parts per billion by mass chloroform. So this is drinking water. A, how many chloroform molecules would be present in a 350 milliliter glass of this water? And so here, part per billion, we kind of do the same thing, you know, as part per million. We just say 0.8 grams of chloroform per billion grams of water. And so if we multiply this by billion parts ppb, then we get 0.8 ppb. Sometimes you can't avoid doing two equation, two unknown problems. Like in number 92, a 0.732 gram mixture of methane and ethane is burned, yielding 2.064 grams of CO2. What is the percent composition of this mixture? A, by mass, and B, on a mole basis. So maybe I'll do 92. What did I ask on the test? What I asked on the test was, methanol and ethanol. Well, methanol and ethanol is one step harder. Let's do methanol and ethanol. We'll do number 39, which is, I think, a little bit harder than the one in the homework, but not by much. Two-component mixture. When we have a two-component mixture and we want to know the composition of that mixture, I told you there are two ways of doing it. Does anybody remember the two ways of doing it?
Empirically or graphically?
Yeah, well, empirically it will just say, you know, two equations, two unknowns.
Formulaically or graphically?
Okay, yeah, we're going to do it. I prefer graphic. So we're going to use the graphic method to solve this. And so this is a multi-part problem. What is the formula for methanol? Methanol is going to be the simplest alcohol. What is the formula for that?
CH4. CH3.
CH3OH.
CH3OH. And so we need to know how many grams of this. Okay. And then we are going to have ethanol. What's the formula for ethanol?
C2H.
CH3, CH2OH.
Okay, there are different ways we could write it. We could do CH3, CH2OH, or we could do C2H5OH. Those are common ways. And we need to know how many grams of this. But we do know the total. And so what we can say is X grams of methanol plus Y grams of ethanol is going to equal 0.220 grams total. And so we have two unknowns so far.
I'm
So we need two equations. So what's the other equation? Well, I'm not going to do the two equation, two unknown. I'm going to use the graphic method. Well, how do I use the graphic method again? Does anybody recall how we did that in class? In the graphic method, we make an assumption. Here, I don't know how many grams of ethanol or methanol I have, but what I'm going to assume two things in doing the graphic method. All right, I need to do this quickly since there's not much time. Okay, so the graphic method, one, you assume one extreme, and then you assume the opposite extreme. And so what we're doing is we're doing this. If we know the two extremes, one extreme's here, the other extreme's here. If we know the two extremes, then it lies somewhere in between the two extremes, right? And that's the graphic method. Because graphically we can see one extreme lands here, the other extreme lands here. It's got to be somewhere in between. And so, one, I assume 100% methanol. If I assume 100% methanol, then I have 0.220 grams of methanol. Is that correct? No. But, that's extreme. I can't go beyond that. I can't have 110% methanol. And so this boils down to a straight stoichiometry problem. In a straight stoichiometry problem, the first thing we need is a balanced chemical equation. And so when you combust methanol, let's go ahead and write the equation for combustion of methanol. CH3OH combusts with what?
Air.
With air. What in air does it combust with?
Oxygen.
Oxygen. Yields what?
CO2.
CO2 plus
H2O.
H2O. Okay, when I balance these, I always leave the single element species last. So oxygen I always leave last. So methanol has one carbon, CO2 has one carbon, balanced. Methanol has 4 hydrogens, I'll need 2 waters. That gives me 4 hydrogens. So I don't want to change the CO2, I don't want to change the water. So I'm going to have 2 oxygens plus 2 oxygens. That gives me 4 oxygens on the right. And this is going to be 1 oxygen plus X oxygens, actually X times 2 oxygens, gives me 4. And so what is X? In other words, this is 1 plus 2X gives me 4.
We can't do that.
What is X?
A whole number. 2/3.
Well, just tell me what X is.
2/3.
X is, okay, minus 1 gives me 3, and then divide by 2. X is 3 halves. Okay, so this comes out to 3 halves, and then I don't want fractions because dealing with fractions in stoichiometry is a hassle. So what I'm going to do is multiply everything by 2. And so I'm going to get 2 ethanol plus 3 O2s yields 2 CO2 plus 4 H2O. That's my balanced chemical equation. Then I check it. Okay, then I just do the stoichiometry. So let's go ahead and do the stoichiometry. I'm going to have 0.220 grams of ethanol. And this is why I asked you to memorize some of these so you can do it quickly. If it's a timed exam, you're under constant time pressure. So carbon's 1201, 4 hydrogens is 404, 1 oxygen is 1600. So this is going to be 5, 0, 10, 12, 3205. And so 1 mole of this weighs 3205 grams of methanol. Now, rewriting this formula is a hassle, so we use this abbreviation for methanol, MEOH. MEOH for methanol. Ethanol, we use the abbreviation ETOH. And so that saves me a little bit of time. And these little bit of time, can add up in the long run. A lot of people say, I'm going to save you more time, not even write any units. But if you don't want to write any units and you get the wrong answer, then you're going to lose a lot of points because there's no systematic problem solving there. And so you want to show your work in case you get the wrong answer. Okay, then from methanol, where are we going to go?
Ethanol.
We're going to go to,
Moles of
Oh,
so we have moles of methanol. We're going to go to moles of
Oxygen.
CO2.
Not oxygen,
CO2.
CO2. So there's 2 moles of CO2 for every 2 moles of methanol. Okay, then from moles of methanol moles of CO2 to grams. Well, there's 44.01 grams of CO2 per mole of CO2. Okay, now how many grams of CO2? If this mixture were pure methanol, how many grams of CO2 would that yield? And so I'm going to get 0.22 divided by 32.05 times 44. Times 44.01. And I'm going to get 0.3021 grams of CO2. Could this mixture be pure methanol? How many grams of CO2 did I get?
No, it cannot because
It cannot be pure methanol because this mixture yielded 0.352 grams of CO2. Do you see that? So it can't be pure methanol. Okay, then we go to the opposite extreme. What's the opposite extreme?
100%.
Also 100%
Or
Yeah.
0% methanol.
Yeah. 0% methanol means 100% ethanol. So we're going to go to the opposite extreme, 0% methanol or 100% ethanol. And so that means I'm going to have 0.220 grams of ethanol if there were no methanol. And then I'll just do the same thing. Okay, ethanol I'm going to have to calculate the molar mass of. So I have 2 carbons. 2 carbons is 24O2. Then I have how many hydrogens?
5.
5? No.
6.
6. 6.06. And then how many oxygens? 1. 1600. So this is going to be 8, 0, 10, 16, 4608. And so this is going to be 1 mole of ethanol. Now, ethanol I'm going to abbreviate ETOH because I don't want to write this over and over again. So this is going to be 46.08 grams of ETOH. And so the grams of ethanol. But now I need the balanced chemical equation because I need to know the mole ratio between ethanol and CO2. So I'm going to write out the formula here. CH3CH2OH plus O2 yields CO2 plus H2O. Okay, in this case I have 2 carbons, so I'm going to need 2 CO2s. And then I have 6 hydrogens, so I'll need 3 waters. And then that's going to fix the oxygens on the right. I'm going to have 4 plus 3 gives me 7 oxygens on the right. And then I have 1 oxygen here. So 1 plus 2x, because I have 2 oxygens for every O2, is equal to 7. So what is x?
We need 3 O2s.
So we need 3 O2s. And then it balances. And so this is balanced. So the mole ratio here is going to be 2 moles of CO2 for every 1 mole of ethanol, ETOH. And then the molar amount is 44.01 grams of CO2 for every mole of CO2. 2 oxygens, 32, plus carbons, 1201.
We get 0.4202.
0.4202?
Yes.
Thanks.
Grams of CO2.
Grams of CO2. So could it be 100% ethanol?
No, it's
No.
too heavy.
No, it's too high.
It's way too high.
It's way too high. And so it's somewhere in between, right?
Right.
Yes.
And so where it is in between is this. This is what I call the graphical method. The graphical method is we just make an equation. And so the graphical method will be, which one's bigger? Ethanol? Which one yields more CO2?
Ethanol.
Ethanol yields more CO2. So I'm going to put 100% ethanol here. If it's 100% ethanol, how many grams of CO2 am I going to generate?
0.4202.
0.4202. And so this is 0.1. Okay, if it's 0% ethanol, it's 100% methanol, and how many grams will I generate?
0.3021.
0.3021 grams. And this is a linear, because there's no squared, no cubic terms, no square roots. It's linear. And so all I do is I do a y. Y is my grams of CO2. is equal to mx plus b. And so grams of CO2 is equal to m, the slope. So the slope is going to be delta y, and so that's going to be 0.4202 minus 0.3021 grams of CO2 divided by delta x. Delta x is 100% minus 0%. And so this is 100% minus 0. Actually, let's just do 100 minus 0% ethanol. Times x. X is going to be the percent ethanol. Times the intercept, or not times, plus the intercept, 0.3021 grams of CO2. Okay, so my known is the grams of CO2. So I'm going to plug in the grams of CO2 here and solve for x. So plug in my y, solve for x. And once I get my x, then I'll have the percent ethanol. Once I have the percent ethanol, then the rest is methanol. Okay, does that make sense?
Yeah.
So this is a 2 equation, 2 unknown, but using the graphical method here. All right, so chapter 3 isn't stoichiometry, but this is a stoichiometry problem. This stoichiometry problem probably should have been put in chapter 4. But anyway, since this is in chapter 3, you might see it. And combustion analysis is in chapter 3.
Oh, I got it. It's about 43% or less.
Okay, thanks.
43%. Yeah, I got 0.35283 for percent with the 43% ethanol, which puts us at like 0.353.
What was the answer?